Hello everyone, and welcome to another Leetcode video. Today we're looking at the problem, find minimum time to reach last room 1, which was question 2 in weekly contest 422. So the question reads that there is a dungeon of n by n rooms arranged as a grid, and we're given a 2D array move time of the same size, where move time ij represents the minimum time in seconds when we can start moving to that room. So this will be important to remember as we go forward, that this is not the time that we go to the room, but the time that we can start moving to that room. We start from the room 0, 0 at time 0, and can move to any adjacent room that's either horizontally or vertically adjacent to us, and moving between those rooms takes exactly 1 second. So we want to return the minimum time that it takes to reach the bottom right corner of that grid. So looking at an example, we have the grid 0, 4, 4, 4, and our output is 6 because it takes us 6 seconds to get to the bottom right corner. And we see that because at time 4, this is the first opportunity that we can actually move anywhere, because both to the right and below our starting point are 4. So we can move at time 4, but it still takes us 1 second to get to either of those spots. So at time 4, we can move from 0, 0 to 1, 0 in 1 second. So now at 1, 0, we're at time 5. From here, we can move to any other cell, since we can move to them starting at time 4, but it still takes us 1 second to get to that final cell. So from t equals 5, we move to 1, 1 in 1 second, with our total time being 6 seconds. So a lot of people might try to approach this problem using dynamic programming, but unfortunately for this problem, it will not work. And why is that? So if we think about memoization, we have to store all the different pieces of state that we are tracking in memory, right? So if, for example, we have 3 different variables, say x, y, z, that we're tracking in our memoization, that means we have to essentially track x times y times z. So thinking about this, we can look at the constraints of our problem. So we would have to store the position that we're at in the grid. So we could do 50 times 50, and this represents our row and column. But where things kind of break down is this move time, right? We also want to keep track of the current time that we're on, because there's no constraint that we have to only visit a cell once. We could go back to it. We could get to it multiple ways. So we also need to keep track of not only the position that we're at, but also the time that we get there. So here we also have to multiply this by 10 to the 9. And this is where things become pretty bad. So we'd have to basically take this. If we multiply this out, we actually get 10 to the 11 being our total constraint, because it's 10 to the 9 times 10 times 10 here, we get 10 to the 11. So this is going to be way too much memory and take way too much time for dynamic programming. So we have to think of a different way that we can approach this problem. So instead, what we're going to use is Dijkstra's algorithm to find the shortest path in this graph. And shortest in this particular problem means the one that takes the least amount of time. I'm not going to go super in-depth into Dijkstra and the theory behind it, but I will link some helpful resources in the video description so you can take a look at those. So essentially what we're going to do is we're going to use Dijkstra in this case to find the shortest path to get from our starting point to the bottom right. So what does that look like? Well, we're going to actually use a heap in order to process certain edges in a particular order, and also keep track of the distances or how much time it takes to get to each specific position in a hash map here, and kind of walk through how that works. So we're going to start at this initial position. So this is our time, this is our row, and this is our column. So essentially what we do is we could pop this off, and we'll see that to get to row 0 and column 0, it takes us 0 time. So we can store it here. Now, what this is telling us, and the way that Dijkstra works, is that when we see this for the first time in our heap, we know that this is the shortest possible way to get to this position, right? So when we see this for the first time, position 0, 0, we know that whatever time we have is the shortest possible way that we can get there. So what we can do is we can record it in our distances and then move on. So from here, now we want to go to all of our adjacent positions. So what we could do is remove this from our heap. So now what we'd have is this heap here, and this represents the positions that we can get to from 0, 0. So we have 5 as our time, we have row 1 and column 1, and we also have our time as 5 here with row 0 and column 1. So why do we have 5? Because you'll see that in the actual grid, we have 4. Well, remember, this is the time that we can start moving to these adjacent cells. So we're going to be at position 0 until this time 4, and then it still takes us 1 extra second to actually move over there, right? So we start here, we have to wait until time equals 4, and then we can move to this position in 1 more second. So we represent that by just adding 1 to whatever time it takes. So we use the heap because we want to make sure that whatever edge we're processing is actually the one that has the least amount of time. So again, we'll take this, we'll pop it off. We'll see that we're at position 1, 0 with a time of 5. So here we could say that to get to time 1, 0, it takes a time of 5, right? And because of the way that Dijkstra works, we know that this will be the shortest path possible to get to this position. So again, we'll pop this off, and then we can go through its neighbors. So say we're at 1, 0 now. We can go to our neighbors. Well, we can go up to here. We shouldn't really do that because we've already seen it in our distances, so we can continue past, or we can go to this final position. So again, what we would do is we'd have to look and say, we can start moving here at 4. Well, we're past 4 now. We're at 5, right? So what we would do is say we're at 5. It takes us 1 second to move here, so we'd be at time 6. So really what we're doing is we're going to use Dijkstra's algorithm here to find the shortest path to get from our starting position to the bottom right of the grid. And we'll see that the time complexity here is much better than for dp, because the time complexity of Dijkstra's is O of v plus e. This is the time to actually go through the whole graph times log of v, right? Which is the log comes from our heap and having to rearrange that every time. So we'll see that this is a much better time complexity than that we get with dynamic programming. So let's look at the code and see exactly how we could solve this. So the first thing we do is set up our Dijkstra's algorithm. So there's really 2 main things to make it work. We have our distances, which is going to record the shortest distance that we've seen to get to any position in our grid, and also our heap, which we're going to use to process the edges in a particular order. So the first thing we do, we're just going to push our initial position onto that heap. So this is going to be the current time first, then our row, then our column. So now we're just going to process these edges while there's things in our heap. So we're going to pop off whatever's on the top. We're going to take our current time, row, and column and save them in variables. If we've already found a path to get to a particular location, we don't want to compute it again. Remember, this is because in Dijkstra, the first time we actually get to that position, we know that that's the shortest possible one, just because of how the algorithm works. So if we see a position that we've already recorded a distance for, we don't want to do it again because we know that it's going to be longer than that one, and there's really no point in doing it again. If we haven't seen it, we're going to record it in our distances because we know that this is the shortest path to get to that position. So then we go through all the neighbors. We're just going to check if they are in bounds. And then what we want to do is calculate the new time that we're going to put into our heap. So we're going to start with whatever our current time is. If the current time that we're at is greater than or equal to whatever the starting time we can go to that position is, so say for example, we're at time 6, but this new cell only requires a time of 4 to move to it, well, we can just add 1 to our current time because we're just going to take 1 second to travel. We don't have to wait for any time. However, if this condition is not true, it means we have not passed enough time to actually move to that cell. So in that case, we have to wait for that time to come so we could take that value from the grid and just add 1 to account for the travel time to actually move over there. Then what we do is just going to push that back onto our heap. So then after we process everything, what we're going to do is just find that ending position the bottom right of the grid from our distances and return that. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.